No worries.
So come on in. All right. So for our last talk of the day, and I think also of the conference, we're really happy to have Professor Margaret Murnane. Her and her husband, Henry Captain, run a research group here at GILA, as well as the company, KM Labs. And today she'll be talking to us about the light science of coherent X-rays, how quantum dynamics solves a 50-year challenge. So let's give her a round of applause.
Thank you. Thank you so much. It's a real honor to be able to present today. The first conference I went to in the US was an OSA conference in Boulder, Colorado. That was way back in early 1984, and at the time I never thought I would end up actually teaching here. So it's nostalgic to give a talk at a Boulder OSA conference. And so as you heard, would like to talk about the light science of coherent X-rays, but in particular for work in our group, want to make the point that all of our work is done in teams. The work is technically difficult. We do a lot of applications, and it's something that you really can't do by yourself, and not even as a single professor. And so Henry and I met in graduate school, and we solved the two-body problem by starting a joint research group. And what that allows you to do then is cover a broader range of topics. But of course, the people who really do the work, this is an older picture, so many of the folks here are, have gone on to positions all over the world. But I'll mention the people's names as I talk about their work. So the other thing I wanted to make is that that now the beginning of the 21st century is by far the best time to be a scientist. If you compare when Henry and I did our PhDs, we didn't have the World Wide Web. So you used a landline, you sent a fax, or you sent a letter. You went to the library to look up the backward citations, whoever was referencing your journals. The pace of science was much slower. And the tools we had available were nowhere near what we have now. There was no way to look at the individual positions of an atom. The computing power, has increased by 8 or 9 orders of magnitude, and still growing. We have amazing tools to look at either the ultra small or the ultra large or the ultra old, in that case. But in many ways, what science needs to do for society is also harder. So we actually need these better tools. Clean water is an issue even in California. We used to think only in the developing world, but now with climate change, it's also an issue here in the US. Clean energy is also very important. We need better personalized medicines. And if we're actually going to solve that challenge, we're going to need scientists, engineers, academics, business people working together. And we also need better tools. And that's the research area we do in our group, trying to make tabletop sources of coherent X-rays. And it's sort of also very nice to look at how light helped us to understand our world. And of course, to a lay person, most people can see, so we understand the world by looking around us, making sense of it through light. And you could argue, particularly from an OSA person point of view, that actually light was very critical because our whole modern understanding of nature started with Maxwell's equations. And I found this very interesting quote from Maxwell's: in a few years, all great physical constants will have been approximately estimated, and the only occupation which will be left for men of science will be to carry these measurements to another place of decimals. Of course, Maxwell at the time thought, and he did, he had these beautiful set of equations that could describe light. But it was also light that forced us into the quantum world, because think about it was trying to explain photo emission and trying to explain the fact that atoms emitted very pure colors, when an atom underwent a transition that forced us to Einstein, Planck, and others to invent quantum mechanics. And then, as in many cases, if you're in science long enough, things come full circle, because now what's happening is quantum mechanics is helping us to develop better X-ray sources. So it's sort of one of those, you see many circles as you get older in science. And so what we can do now is, by harnessing quantum mechanics, we can change the color of our driving laser and generate X-rays where we can tune their wavelength, their line width, their polarization, their coherence, and their pulse duration. And that's something that when I was a graduate student, we would have never thought possible, because there was no such thing as an X-ray laser back in the early 80s. There was no way to make a coherent beam of X-rays. And it turns out this capability is very important, not only because it represents light science, which we all love, and trying to exert control over light, but it turns out that in the X-ray region, we have nowhere near the nice optics that we have available in the visible, where we can have wave plates, polarizers, filters, and those things work fairly efficiently. So changing the state of light from its polarization or such, or nonlinear optics in general, works very well in the visible, does not work well at all in the conventional sense in the X-ray region of the spectrum. So this is a very important capability, and how we get there is to start with the laser. We had great celebrations back in 2010, because it was the 50th anniversary of the laser, and of course it started out, as you all know, as a solution, as being called a solution looking for a problem, but now we do laser eye surgery, powers the internet, beautiful science, and many applications. And of course, what makes laser light special is its coherence, the fact that you can make a directed beam and control its properties. But it's also historically interesting to realize that the first laser that was demonstrated by Mayman had a color, it was the ruby laser, a color 694 nanometers. And in the 55 years since the demonstration of the laser, the shortest wavelength laser that is in widespread use is the excimer laser at 193 nanometers. So, you see those beautiful orders of magnitude increase in computing capability or in data storage. In light, in terms of laser light, in terms of sources that are in widespread use, we've improved them by less than a factor of 4, which is sort of quite surprising, and I'll explain why. But so what we're trying to do in our research group is develop short wavelength lasers that have some chance of being able to impact technology in a broad way. So of course, there are X-ray sources in widespread use. Whenever you go to your dentist, or if there's any, suspicion of a crack or something, you'll go for an X-ray. And what is remarkable is, if you look at the quality of the X-ray that for example, your radiologist might be looking at, or your dentist, it actually doesn't look a whole lot better than that first X-ray that Röntgen took of his wife's hand. And actually the technology, it's a more powerful version, but it's basically still an X-ray tube, which is basically still an X-ray light bulb. So you're taking a picture with incoherent light. We just heard why coherence is always better if you want to image something. And so there's great motivation, better X-rays, many other applications if we could make a coherent version of the X-ray tube. But it's very hard. So it's not because our community is dumb or doesn't work hard that it's been 55 years and we still haven't figured out how to do this. Actually, the basic physics of why it's so hard was understood way, way back. To make an X-ray laser, you have to put an atom in a highly excited state. The lifetime of a highly excited state is very short. So you have to put an enormous amount of power into a medium to make a population inversion. And if you do the math, it turns out that power requirement scales as the wavelength to the inverse fifth power. And so what that means is that I can hold, a laser pointer in my hand because I can power it off batteries. But if I want to make a laser with a 1 nanometer wavelength, I need a terawatt of power. That's on order of the electrical generating capacity of the United States. So nobody is going to make a continuous wave X-ray laser. It's just not possible. And if you want to go to 1 angstrom, then you need a petawatt of power. And it's for that reason that way back in the 80s, for those of us senior enough to remember the Reagan Star Wars era, at that time, scientists proposed to shoot down missiles by detonating a nuclear weapon in space and driving an X-ray laser. So of course that not so practical, all right? And it's also for this reason, this very tough scaling law is why the first X-ray laser was based on a different technology, not on population inversion, but rather electron acceleration. And this was the free electron laser that was demonstrated at SLAC pretty much 50 years after the demonstration of the visible laser. It works beautifully. It generates a millijoule of coherent X-rays at a repetition rate of about 20 hertz. But Steve Chu was the Secretary of Energy at the time, and we were having all these celebrations because of the 50th anniversary of the laser. And Steve says, it's a marvelous machine, but it's definitely not free, and I should know it, because of course it costs about $1 billion. So, and it's also not small. This is the electron accelerator. This is the freeway interchange near SLAC at Stanford. So this is a 2-kilometer long accelerator. There's certainly ideas to scale this down, but it's still quite expensive, and you're definitely not going to be able to build one of these at every fab or in every hospital. It's just not scalable. So in our group, we're looking at techniques that maybe won't generate as much energy, but we can generate enough average power to be able to do applications. And so what we do is we try to push nonlinear optics to an extreme. Now, we know in nonlinear optics, and it's remarkable how rapid progress was back in the 1960s, because only 1 year after the demonstration of the laser, Peter Franken took a ruby laser, focused it into a quartz crystal, and got out the second harmonic of the ruby laser. And we know why this works, because we have a sinusoidal field, but in a crystal, the motion of the electron can be anharmonic, so you get higher order harmonics radiated. But for 30 years, you could only get a few harmonics with very rapid diminishing strength. And so that was the case with nonlinear optics for about 30 years. And then a somewhat accidental discovery in the late 1980s in Chicago, in Charlie Rhodes' group. So they were taking these, at the time they were new, femtosecond lasers, and focusing them onto anything and to see what happens. And so he took an excimer laser and focused it into a gas, and to their surprise, what they saw is the 17th order harmonic. Nobody had ever seen the 17th harmonic of light, so knew immediately something was different was happening, and it took another 6 years to figure out exactly what was happening. So, and that's shown here, that essentially if you focus a femtosecond laser onto atoms in a gas, then due to the strong field of the femtosecond laser, you're going to depress the Coulomb barrier that binds the electron to the atom. The electron can undergo tunnel ionization, get accelerated away from the ion, and then when the laser field reverses, it can return to the atom and undergo a coherent recombination and generate these beautiful harmonics that have now been observed up to the 5,000th order. And you can also think about this process as what you might come up with if you took the Röntgen X-ray tube and decided to try to make it coherent. So think about, how does an X-ray tube work? You run current through a filament, thermionic emission results in emission of electrons, accelerate them in a strong static electric field, and when they hit a target, you get Bremsstrahlung. So essentially, this high harmonic generation process is the quantum version of the Röntgen X-ray tube, because we boil electrons off an atom using a strong femtosecond laser field. We accelerate them in the laser field. And then the third step is also coherent because the electron recombines with the part of the wave function that is not yet ionized. Our collaborator from Salamanca made us this nice quantum movie of actually what's happening. We're making a nanoscale quantum antenna. So as the electron is driven back and forth in the laser field, the wave function acquires these beautiful quantum interferences, and those quantum interferences in the electron wave packet, as they're driven by the ion, looks as if you're accelerating that electron with much higher frequencies. And so that is the physical origin of this light. And that was well understood, and the quantum nature and everything worked out about 20 years ago. And what was harder is something that us optics folks would sort of say, you know, that might not be all that hard. What was harder is not how do you make one atom emit harmonics, because so this is just showing in time what's happening. You have your laser field. On the leading edge of the laser field, you start to ionize the atoms, and you get X-rays while you're ionizing the atoms. So the X-rays you make are always shorter in duration than the laser pulse you use. And then you get a nice emission, but it's a dipole transition, so you will not get a beam, all right? Dipole emission has this very broad direction, and that's what you get from each atom. If you want to make an X-ray beam, you have to figure out some way of adding the X-rays from many atoms in the medium. So how do you do that? And you might think, how hard could that be, you know? And so what you have to do is force, so the laser comes in, generates an X-ray from one atom, and if the two colors travel at the same speed, you will get constructive interference and a bright X-ray beam. How hard could that be? Well, this is another little image from Carlos Hernandez Garcia. And so he made the nice analogy that it's as if your laser beam is a quantum conductor, and you're trying to make the number of atoms equivalent to the number of people on Earth sing in tune. And not only that, but they have to, the laser wavelength this is not to scale. So this laser wavelength can be up to 4 microns. The X-ray wavelength is 1 nanometer. So you have to add these fields with sub-angstrom spatial resolution and sub-attosecond time resolution. And there is no way. We don't have electronics that can let us do this. There's just no way. So it forces us, we have to understand the quantum physics and see if nature will help us. Because nature has to do it passively, because we can't control light to this kind of precision. And fortunately, it does work. So what happes is you focus your femtosecond laser into a gas on the leading edge of the pulse. Of course, we know light, whenever it goes through a material in the visible region, it always slows down. But we also know materials don't bend X-ray light, so you know that the refractive index in the X-ray region is 1. The phase velocity is c, the speed of light. So on the leading edge of the pulse, the laser light is going slower than the X-ray light. But when you ionize the material a little bit, it turns out that the speed of light in a plasma is greater than c, the phase velocity. So there's a time interval during which both the laser light and the X-ray light are both propagating with the same speed, given by the speed of light, and that's where you phase match. And so phase matching is temporal in the X-ray region for this process. It took people a while to understand this, because think about all our intuition was using birefringent crystals to optimize phase matching. It was spatial. You were achieving phase matching through a spatial constraint. Here it's a temporal constraint. So it took a while to understand the physics, but fortunately we do understand now how it works, and so we can make these nice plots of as we change the driving laser wavelength from the ultraviolet through the visible into the near infrared region. These graphs here show the lines show the predicted phase matching limits, and the dots show where we've experimentally verified them. So for example, using Ti-sapphire lasers, we can make bright harmonics into the extreme ultraviolet region of the spectrum. And as we go to mid-infrared driving lasers, those increase into the soft X-ray region of the spectrum. And it does actually work. If you change the color of the laser that you focus into the gas, you get different color X-ray beams, although only CCD cameras or other detectors are sensitive to them. But you get these beautiful beams that, in fact, are as good quality as many a laser beam that we would use. And this is a picture of the team that demonstrated most of this work experimentally. They were led by Tenio Popmichev. This was his thesis work. And so in our labs here at Chile, we had 800 nanometer light, 1.3 micron and 2 micron light that let us make X-ray beams into the to about ½ kV. And then our collaborator Andrus Baltuska in Vienna had a very nice laser around 4 microns, and that allowed us to make coherent X-rays up to above a keV. And it's quite a remarkable source. It is the only way to make a coherent soft X-ray beam on a tabletop scale apparatus that's been demonstrated to date. Each of these photons are about each of the mid-infrared photons are about 0.3 eV, so at 1.6 keV it represents a 5,000 order nonlinear process that's phase matched. This spectrum spans 12 octaves, and to even be emitted, everything has to be synchronized to attosecond durations. It just would not work. You would not even see a beam if that were not true. And from a spectroscopic point of view, it's great. It spans all of these characteristic elemental absorption edges. So it's very, very interesting for material science, chemical science. And although I'm not going to have time to talk about it, it generates these ridiculously short pulses, actually shorter than any process in nature, in the natural world. This is a measurement very like we heard Professor Teich talk about, some of these interferometry. So we use a version of this to show that, sure enough, our predictions of these isolated attosecond pulses being able to sculpt the spectrum in time and frequency were actually true. Won't have time to talk about it, but it is remarkable that you can focus a 40 to 80 femtosecond laser into a gas, and you get out a sub-femtosecond isolated pulse. And it's all due to this wonderful quantum physics. And then more recently, working with Oren Cohen's group at Technion, we and all our community realized that we can actually have even more powerful control over the X-ray light. In the past, everybody thought, well, because you're driving this charge, this electron, with the linear polarized laser, and then it will rescatter, you get these nice quantum interferences, and you get X-ray emission. But if you used a circularly polarized laser, you'll ionize the atom, but because the laser is circularly polarized, the electron will never return. So all of us experimentalists thought that we could never make circularly polarized X-rays because you couldn't get the electron to return. If it doesn't return, you don't get an X-ray. It turns out we were wrong. There was theory papers in the literature since 1995, so 20 years ago, and they had proposed using two-color lasers. And if you used a two-color laser, this is what happens to the poor electron. That you start to ionize and it circulates, but it does return. And it's a little bit more intuitive if I show you the electric field. So what we're doing is focusing, instead of one color linear, we're using a two-color circular where the two colors have opposite circular polarization. And then when you combine these two fields together, you get this cloverleaf field, which of course does drive the electron back to the ion. And then you get this quite amazing conservation, because we also always have conservation of energy, that depending on how many laser photons you add up, you get an X-ray photon out. But now you also have to conserve the spin angular momentum, and your X-ray can only carry out off plus or minus 1 angular momentum. So what that means is that you can only absorb one more red than blue photon. So you get, and then that gives you a crazy spectrum where every third harmonic is left circularly polarized, every adjacent harmonic is right circularly polarized, and the one next to it is missing because it doesn't conserve angular momentum. There is no visible light source that makes a spectrum like this. So we got our resident artist at Jula to try and make a nice picture. And so what's shown here is this is the artist's rendition of the cloverleaf driving laser field. Then the electrons are green. We all know electrons are green, and they come out, you know, where the cloverleaf peaks, and then the X-rays are blue. So this is sort of an amazing, and although I won't go into the details, so not only does this work for every single atom, but the phase matching is actually also works. And so this was very, very nice, and we were delighted that the Science picked this as the cover for the special issue associated with the International Year of Light, which we know is this year. And then more recently, we've shown that we can extend this into the soft X-ray region using different color lasers. Again, these amazing spectra that have left and right circular polarization, and we can apply this in magnetic materials. And then in work with Chip Durfee's group at the Colorado School of Mines, it actually can get even crazier, because now instead of sending the two colors lasers propagating together, what if you now change the angle between them? And then if you do that with circular polarization as well, now you start to restrict what combinations are allowed and what directions are allowed. So that's also really neat, because again, we don't have good X-ray optics, so if you can use a visible laser to control the direction of an X-ray beam, that is really neat. So this is the photon picture that Chip and Dan Hickstein from our group made. So you can sort of see if you cross two circularly polarized lasers, and again, each harmonic can only absorb, you can only have, you know, left or right, you can only have a plus or minus 1 helicity. So that means you can only absorb one more photon from one beam than the other. And as you add more photons, you can see you're going to get a different angle. So then the harmonics get emitted in the forward direction, but each harmonic has a different direction. And so in principle, you can use that to separate all the left circularly polarized harmonics go in one direction, all the right circularly polarized harmonics go in the other direction, and each harmonic is spatially separated. We're still exploring this, but it's kind of neat. This is something we did not expect from conservation laws. And so I think I must be almost out of time. Is that right? Really? Oh, okay. Okay, well, yeah, I know people must be getting hungry, but I'll finish up in 10 minutes. So I hope I've convinced you that we now have light sources that are really faster than any dynamic process in nature. Because if you look, you know, so of course, you know, the macro scale, of course, is static, you know, compared to our pulses. But even if we look at vibrations in the, you know, of a CH bond, that period is only 8 femtoseconds. And even if you start to look at the dynamics of highly excited electrons and Auger decay, that's still got maybe a 10 attosecond limit. So we really, you know, have this because we have a coherent bandwidth, and we know that fundamentally the Heisenberg uncertainty principle, or Fourier transform, has to apply. All right. So we like, you know, the femtosecond folks like writing down the uncertainty principle in its femtosecond energy, time energy expression, where if you express time in femtosecond multiplied by bandwidth or energy scale in electron volts, that's about 2. So Ti-sapphire lasers have a bandwidth of a fraction of an eV, and that is why Ti-sapphire lasers give you about 5 or 10 femtoseconds. But now we have a 3 order of magnitude broader coherent bandwidth, so we can make a 3 order of magnitude shorter pulse. But I also want to just caution, because a lot of people misunderstand attosecond science, because of course the same is true of the energy scale of the process you look at. To have an attosecond phenomena, you have to be talking about something with keV energies. So in general, you're talking about the dynamics of highly excited atomic states. And most chemistry and materials, they occur on energy scales of about an electron volt or a few electron volts. So those time scales are on order of femtosecond on up. There's a few special things that happen below a femtosecond. But we still care about the bandwidth, because if we want to look at dynamics at multiple sites, we want to be able to look at carbon, look at oxygen, look at nitrogen, and see everything happening at the same time. So we do want the coherent bandwidth. And that's actually, people can have differing opinions, but in my opinion, that's the sort of the exciting aspect of these new light sources. And of course, as well as having very short time scales, the wavelength is also very short, well matched, perfectly matched to the nanoworld. And then on top of that, X-rays can penetrate somewhat. The penetration power gets better the higher the photon energy you have, but they also have these characteristic absorption edges. And what I'll talk about is the new capability in imaging, which we're very excited about. But just to give you sort of the 40,000-foot view, really what we're learning is that with these tabletop X-rays, we can do some really interesting material science, and we can look at the sample multiple times to really understand what is going on in these samples. So that's a different mode of operation than people have been doing at the synchrotrons, where you propose something, you get a week, you go, you take your data, and you can check back again maybe 6 months later if you're lucky, if you get another beam time. And so what we can do is, take a sample with our collaborators, investigate it. We see something funny that we don't understand. We can hypothesize, maybe it's this, maybe it's that. Let's make a few different samples. Let's check out what's going on. And it's interesting, in all cases, had we written up the paper after the first week, we'd have gotten the wrong explanation. So this access is actually very important, especially in science. And we were just talking about not exactly the irreproducible results, but the failed experiments. So one way to sort of mitigate that is if you can do the experiments many times and carefully, you can be more sure of what you're seeing. And so lots of new discoveries in material science, but the one I want to talk about is in imaging. And so of course, using multiphoton and super resolution imaging, you can make these amazing microscopes using light. With X-rays, we're not quite so fortunate because, of course, we just said that no material bends X-rays, so you have to use diffractive optics, and they're very limited. But fortunately, way back in 1952, so before even the laser was invented, David Sayer proposed that if you had a coherent beam of light and shine it on an isolated sample and collect the diffraction pattern, then under certain circumstances you should be able, of course, the amplitude of the Fourier transform. If you knew its phases, you could recover the object. But if you have the right phase retrieval algorithm, you can recover the phases and recover the object. And one of the things that allowed one to do this initially was if the object was isolated, what you could do is take the experimental scatter pattern, make a Fourier transform by just guessing at the phases. But of course, if it was a first guess, you didn't guess right, and so you will recover some object that's not in the region where you knew your sample to be. So you needed to know something about the sample initially, but you know that that's not real. It's due to an incorrect guess of the phase, so you can set the amplitudes here to 0, make another Fourier transform, compare the retrieved scatter pattern to the experimentally measured one. If it doesn't agree, replace it by the experimentally measured one, keep the phase, and then iterate until you get, hopefully, some convergence. And the first person to do this in a 2D sample was John Miao using the Brookhaven synchrotron. And the thing I think that's cute about this story is that David Sayer was a co-author. So almost 50 years again. But sometimes it takes a while for the technology to catch up with the idea. And initially it started out as people saying, you know, anything that you have to guess at and you have to put constraints on your object, it's never going to have a really widespread application. But just like with the OCT that Professor Teich talked about, so here it took a while to develop, but now it's very clear that it's actually better than X-ray microscopy that uses zone plate lenses. I won't go into the details here, but it's getting better and better. And in our group, what we were able to do was develop a reflection mode microscope. At synchrotrons, it was being used to image cells, for the most part, objects in transmission. To do an object in reflection, it's actually a little bit more tricky, so we had to use some special techniques. But now we have a nice working microscope where we shine one of these harmonic beams onto a sample, raster scan, collect the diffraction pattern, and then we get a very nice image of the sample. It uses this overlapping images. So instead of this sample, of course, is not isolated. So we cannot use the isolation constraint to help us guess the phase. But instead, we use a technique called tychography that uses a series of overlapping images. And then there's only one beam and one sample consistent with the multiple of overlapping images, scatter patterns that one can extract. And this is the team, Dan Adams and the imaging team that did this work. And we're very proud of this series of images because what it does is it compares the amplitude and phase images of an object using our coherent diffractive imaging microscope compared with the scanning electron microscope image. And what you can see is that the phase image using our coherent microscope actually picks out a lot more details of the silicon sample than does the electron microscope. And this is not surprising because in an electron microscope, you're relying on the different reflection of the X-ray beam on the sample to get your contrast, whereas of course we're using light, short wavelength light. And of course, so the phase contrast is much higher. And so this is, has a resolution of very close to the wavelength limit horizontally. And because it's a phase image, it turns out that the vertical resolution is much higher than the wavelength, and it's under 5 angstroms. And then this is a movie Dan made showing the phase retrieval algorithm working to retrieve these images. And Dan was able to get the cover of this May issue of Laser Focus World also. Other very sort of surprising things we were able to learn, for example, is if you have an array of hot wires that you might have in a chip, for example, so which, and they're very small structures, nanoscale type structures, which cools faster. You might think that the structure that has the wider space hot spots might cool faster than a structure with hot spots very close together. Turns out that's not the way heat flow works. We can see very clearly on our data that actually a hot nanowire will cool more quickly if it's surrounded by other hot nanowires. That's just got to do with how does the energy flow couple to the phonon distribution in the substrate. So again, this was an accidental discovery. We could not have made it if we didn't have access to a tabletop light source where we could do experiments again and again. And that was work by Kathy Hogeboom-Pop and Damiano Nardi. Okay, so we are trying. I mentioned something about that maybe there's widespread applications. We don't know yet, but we're trying. So this is the scale of the laser and the light source and the beam line. For those of you who are familiar with synchrotron beam lines, this should look small, much smaller than a synchrotron beam line. And we're working very hard on developing lasers that might be compatible with widespread applications. This is what the light source looks like now. We call it the Zeus for X-ray ultra-fast. I should know this source. Ultraviolet, thank you. Extreme ultraviolet, ultra-fast source. And in new work that Tenia just submitted for publication, what he's finding is that there might be more than one route to make KV X-rays, And the nice thing is that if we use ultraviolet lasers, we can make soft X-rays with very nice peaks. These would be great, for example, for the coherent imaging. I just talked about our photoelectron spectroscopies, and that complement these supercontinua that are very nice for spectroscopy. So we'd love to develop microscopes that can image functional materials, still have a ways to go in making the technology accessible. Tenure can do amazing things in his lab, but how to get that into hands of a biologist or a material scientist, that's still a long way off. So we have to work really hard on the technology to make it more accessible. A lot of people to thank. I mentioned the people who contributed to the main keyword, and with that I'd like to thank you for your attention.
Thank you so much for that great talk. And if I have a few seconds, I'd like to say a few concluding remarks. So one thing we've seen today is we all love the experiment of Franken with the second harmonic generation. It's funny, all of the speakers have mentioned it today. And you had mentioned at the beginning of your talk the pace of science. I got the opportunity to see, I think, Henry Captain give a presentation on those circularly polarized X-rays back in April, and you already have some new exciting results since then. So it's true, it moves so much more quickly. So with that, do you have any questions for the speakers?
I have one. I'm curious what light source you're most excited about or think has the most promise for high flux HHG in the future. I think like a fiber-based source or like OPCKs, or I don't know if you
there's so many new things happening that I think we'll just have to run them off against each other and see. All right? There's so many new things. There's clearly many ways to design the source. There's also the cavity-based systems. It could be that for different applications in different regions of the spectrum, there's going to be different solutions, just like we have with visible lasers. All right. But it does seem, I think there's been enough demonstration now, and we don't see another route right now, to make an alternative, if you want coherence. So you don't need coherence for everything, but for very high precision metrology, it's useful. And of course for dynamics, it's by far the shortest pulse anybody can make. So it wins in terms of time resolution, hands down. So it's like, most of you are too young to remember the femtosecond laser LASIK, but back when femtosecond lasers were first developed, people didn't even understand how to measure dispersion in a mirror. So when I was building my colliding pulse mode lock dye laser back in the 80s, because this was before Ti-Sapphire had been shown to make short pulses, the labs had one laser working well in their lab, and nobody could reproduce it because they didn't understand the mirrors mattered, that the dispersions of the mirror mattered. So but eventually they figured out it was that mirror because they would swap out. So they just cut the mirror. So the mirror ended up being cut into 8 on 8 different. And who would have thought now you'd have a LASIK that uses femtosecond lasers to, cut a flap? So it just takes time. It takes 20 years sometimes, from where a technology is demonstrated to where then it gets used in an application. And you see that again and again and again. But that's what makes light so wonderful. If anything, light is more important for 21st century technologies. So, it's a good field to be in. Yeah.
Are there more questions?
Yeah, do you think, so the our lab has its, just, I was curious, is it you're mentioning that this is complex for maybe other field, like biomedical fields?
Yes.
Is it just because of the sheer complexity
of the system? That's right, because the femtosecond laser, you need to know a lot of optics, isn't that right, to operate them. And so that has to be dealt with. And of course, the doctor who uses LASIK has no idea of what the femtosecond laser is. It's in a box. But it's better than a blade. I would trust the laser more than the blade. But it has to be that's the front end. Remember that LASIK, laser is the front end of the amplified system, and then a Zeus, and then
Do you think the flux is there?
The
And if you could make that in like a fiber-based system, for instance, then it would go to like say biomedical fields more easily.
So yes, it should be practical, but what I didn't realize until worked with some companies that we think it's like you do a huge amount of work for a year and you might get a paper, and then it takes another 3 or 4 months to get the paper good, and then but if you look at to get to an industrial application, you have another 10 times as much work to engineer it. That's what is kind of amazing. And you have to find some way of doing that. And that's hard, right? Because there has to be a market need before you can start to do that. So but almost always good technologies do get, if there's a need for them, that happens eventually. But then they have, if they have different champions, or if there's, but the road to commercialization is often very kind of roundabout. Like the companies will always say initially, oh, that's too high tech, that's too advanced, we don't need it. But then eventually the demand builds up if they can't do it other ways. But that's why it's tricky. That's what they call the valley of death with all these technologies, because you got all the good ideas over here in the universities. You got all the business folks saying, if I don't need it, I won't pay for it. And then how do you get it through? And that's why it's any business guy or gal will want to make an incremental improvement on what they have currently. It costs much less. So that's what so it takes a lot of, I think, to get that first femtosecond laser commercialized, I think if I'm not, I remember the number wrong, but I think it took 70 million in investment to get it commercialized for LASIK. It's just amazing, yeah. But of course, but our job is to come up, the academics, we come up with ideas, good technologies, and then if you have a lot of staying power, you'll try and, push it over into the real world. But then some technologies are go faster, isn't that right? So some of it depends on how much engineering. With that initial femtosecond laser, there was all these clinical trials they had to do, and all this, miniaturization and optics and such. So that's why it took quite a while and took a lot of money. But it's interesting, yeah.
Could I actually ask you one question? Hopefully it's not a tricky one. So hearing about the high harmonic generation and multiple octaves of bandwidth is really impressive to me from like a frequency perspective. So I was wondering if you think it would ever be feasible to create, an extreme UV frequency column with, octaves of bandwidth.
I think. Oh yes. Okay. So.
Phase, like pulse to pulse basis, the phase doesn't move, or it moves by 0 or 2 pi, something of that nature. I was just curious.
So I think that supercontinuum. Okay, so you mean shot to shot?
Yes, sorry, yeah.
Yeah. So Tenio happens to be here, so it's great. So was the 4 micron laser CEP stable?
Not to this point.
Not to that point, okay. But in principle,
It's not.
yeah.
So
Yeah.
there is other
Yeah.
technologies.
Yeah.
Okay, cool.
So yeah, that would be an amazing precision. Yeah.
Well, I guess with one quick announcement. So I've been informed that our solar cooker oven outside is working, and we have cookies baking in there right now. So be welcome to stop by and have a cookie whenever they finish. I'm not sure if they finished yet. Okay. So at least stop by and see it. Let's give
Thank you.
Professor Murnane a
Thank you. You guys were great to hang in until the end.
Don't forget your, I don't know if I gave you the laser pointer pen, but we thought
That's-
those were
oh,
super
thank
fun.
you.
Yeah, we
Wonderful,
had
wonderful,
some
wonderful.
up here.
Wonderful.
Is the camera, should I turn it off or is it?
Turn it off, please. Thank you.
It's just the little recording.
Yeah, it's just the big silver and red button.